Good evening, everyone. So this is something I presented inside my company for all the lot of new React developers or people who coming from back end to front end, and I thought this is important for them to understand why they're doing it. So that's how it started. So yeah, let's start here. So this talk is more about just going back to very simple basics, so you can compare with how React does it. So it's going to stay more in the data structure level, and the last few slides I'm going to compare with the React. Yeah. So in order to understand how React works, it's important to understand how even the animation works. I'm pretty much sure everyone has played with this in your childhood. By flip through all the pages and you get an illusion as if something happening. So if you want to design this, what you need? So let's start with the bare minimal state. Let's have a two image. One image is like just in standing position, and another image is in walking. So if I flip between these two, I create an illusion as if something is happening on the screen. Oops. Let's try the same thing for a small, like if pages of multiple images. So in this case, in this page it's empty, and second page I'm adding a character, third page another character, another character, another character, and it creates an illusion as if someone is typing on the screen. So in order to design this, let's name it as an animation engine. So we need an initial state. In this case, the initial state is empty text box and an image with no color in it. And then we add some instruction, and the instruction here is walk, and the second instruction we have here is insert a character yes. And then we add another instruction called color, and then we calculate the coordinates, and then we calculate the layer position of each image, and then we draw them on the screen. So this is the idea behind it. So now this become the initial state now, and to that state we add again instruction. Now the instruction is stand, and add a next character to it, and then we draw on the screen. So like that, keep on going in a loop like this. And this idea is abstracted, and browser is doing this for us. So idea of this loop and creating an illusion kind of thing, that's what browser does for us. And this cycle is called animation frame, and in a second it almost 60 frames runs. So for single cycle, it takes 16.67 milliseconds. So if you go more than that, that's where you see a lagging effect on the screen. You feel like something is not working properly, you feel something is not smooth enough. So it's important for browser to make sure every cycle runs within 16.67 milliseconds to create a very smooth effect. And browser does batch layouts, and how it does, let's have a small example here. So here we have a read operation where we are reading the height of an app, and then followed by we have a write operation on a DOM tree where we are updating the height, and then we have another read operation and then another write operation. So what browser does it, when it comes to the second read operation, since there is a write, it knows it doesn't want to give a wrong value, so it does a layout and then give it for you. So what happens is here there are two layouts is happening. So in order to avoid that, what we can do that is we batch all the write operation. So we do all the read first, and then we start doing the write. So number of layout is going to be 1. So that's how we make sure our browser runs very efficiently. This is easy for a small code snippet, but if you want to do across the entire DOM, like a DOM tree is like 500 elements or 1000 elements or something, you can't just write in a code snippet. We need some kind of an algorithm or something to do this batch writing. So there are multiple techniques here, so I'll stick with the virtual tree concept. So the first thing is we don't want to read directly from DOM. So I'm going to design this idea now with just simple basic data structure. So we read from the copy of DOM, and then we compare every time with the changes, and if there's a change, we do a write operation. So we are not doing any read directly, we're making from a copy now. So let's design this. So in order to do that, it's simple. We need to traverse a tree data structure, and while traversing we need to read, compare, and then write if there is a change. So let's take a small data structure here, so which has a root, and then you have to go to each node. So the relationship we have in the linked list we have here is first child and sibling here. So a root first child is child 1, and then its sibling, and it's keep on going like that. So that's how this linked list is formed. Now when you start with the root, you go through each and every node and come back to the root. So you get this call stack in your browser. So this is a recursion. This is good because we did all the read operation, we can do compare, that's fine. But there is a drawback here. Suppose your tree is like 5,000, 6,000 elements, 7,000 element. You're going to take more than 16.67 milliseconds, and you're going to have a lagging effect. So in order to cut this, what we do is we need to convert this recursion to iteration. Why? Because in iteration we can break the traversal of tree at any point and we can come back at any time. And in order to iterate, instead of we doing in our own loop, let's take advantage of the browser loop cycle. So what we are going to do is we are going to traverse the tree across the browser frames. Instead of doing in a single frame, we are going to traverse the entire tree across like 500 frames or 600 frames, whatever it is. And instead of writing directly to DOM, we are going to collect every changes, and then we are going to commit in a single frame. So in order to do that, browser gives these two events for us. One is an animation frame and idle callback. So what happens is before executing JavaScript code, that's where the animation frame is going to start. Browser will execute all the callbacks which is registered for animation frame, and it has another callback which is like when the browser is not doing anything. Say for example there are 16.67 milliseconds and your code is executed for 10 milliseconds, and then you have like 6 milliseconds more. That's where the browser invokes all the callbacks in idle, and if you want to do something you can do right now. So let's take advantage of that. So you have a lot of chunk of JavaScript code, so you do few nodes in the given time and you do the remaining nodes in the next callback time. So that means the second animation frame. So in order to do that, we have to convert. So in recursion it's always easy to come back in the tree, but in iteration we need to provide a direct relation saying that how to come back. That's basically return statement. In this case it's parent. So our data structure will change like this. We'll have a parent, first child and sibling. This is okay for a fixed DOM tree, but your DOM trees keep on growing by adding a new child and deleting a new child and a lot of things. So we don't want that. Instead we want something like this, where we have a root element and we have a children function which will return the number of children in it, and then we need a function which create this linked list for us. So thereby you give that bottom one which goes through this function and gives this data structure for you, which is basically a linked list. So this linked list, what it exactly has here is basically a wrap one which holds a relation called parent, sibling and value. And this is what we are abstracting out to batch all the changes. So we are building linked list for iteration process, and we are traversing node in idle time across the frames, and we collect changes from this virtual DOM and we commit all these changes in a single frame. That way we make sure that everything runs within that 16.67 milliseconds. And this is what React does that for us. And the wrap element is what the fiber node, which hold the instance, which is the React instance where you can see all the React state, props, render function and everything, and the relationship. So fiber node is basically a relationship between all the children's, which is going to generate when you call render function. So React builds this linked list by calling your render function, and whatever is returned from it, and that's where it starts forming a relation. So in this case there are two children, so first a sibling relation between those children is formed, and then a return relation by setting the parent, and then returns the first child. And that's how React traverses each and every fiber node. So I put a small example here, let me show that. Oops, what I did. So this is not the exact React code, but it's something similar to that.
Could you make the font bigger maybe?
Oh yeah.
Can folks see?
It's good enough? So let's have a code walkthrough here to see how React builds this tree. So React is not basically making any copy of DOM. Instead, from those render function, React builds the entire tree from your render function, and that starts as the initial tree for you. So as I said, React every time goes and check, do I have some idle time with the browser? And that's what it checks. Do I have some idle time? And in this case, yes. So I tried to get the children by calling the render function. So in this case, the render function returns a list object, a list React element, and then it creates those linked list for you. So here the linked list app first child is list, and the return element is parent, and there is no sibling for it. So it returns the first child as the next unit of work, and React goes and check, do I have still more time to do something with this node? If yes, React goes and execute that function and goes and call the render function of the list. In this case, it returns 2 item and 1 button element, React element, and then React builds the linked list for that. So in this case, the first child is item 1, and the sibling for it is item 2, and the sibling for its button, and the parent of all the 3 has been link is created. And then React returns the first child here. So in this case, the first child is item, and then it again goes and checks, do I have some time? If so, it's yes, and then calls the render function here. And in this case, it returns 1 and 2 React elements, and it just keeps doing that. And yeah, so in this case, what happens is it doesn't have a first child, so that means there is no more relation for that. So it completes the unit of work, and that's where React calls the component did mount and whatever the function. So basically, it's a post-order traversal happens here, and that's where React does with what the thing it wants to collect changes. It collects the changes, and all this information is done here. And then goes and returns the parent sibling, next sibling here. The sibling is 2, and then there is no furthermore sibling or there's no first child for it, so it just returns the unit of work for it. And then it goes and gets the parent sibling. So before it goes and gets the parent sibling, what it does is, okay, I finished all the children for you, so your work is done. Now we can go and update for the items. So that by React, what it does is, now it's traversing back. At that point, okay, is there any changes? It goes and makes an update to its update queue here. So that's all done in this post order code. And then React goes and gets a sibling. Here it gets the parent sibling now. So 2's parent sibling is item, and that's how it's keep going. Let me get to the end of it. Oops. Yeah. So once it gets everything, React goes and commits to the DOM, and that's where it creates the first DOM tree. So this is a HTML element for it, and this is what React does for us. So what exactly we are doing here is, so DOM tree is communicating with the render tree through the API, and we use get element by ID and those kind of API to communicate with DOM tree. That's what React is doing on behalf of us. And instead React gives these APIs, render, set state, use state, and component did mount, which is in hooks is use effect. Use these to make those changes. So React does this DOM API update for you instead of we doing it. And that's what I mentioned, data structures behind batching, and this is how we React batch changes to help browse the batch layout. And to get better understanding, I highly recommend to go to this video. And then in Medium, he has did a good job in breaking the code, how React in depth does this state and props and those kind of updates. I recommend these two links will guide you further. That's it. Thank you.